All right, we're going to look at one more problem here. This is Chapter 5, Problem 8. And in this problem, there's a person walking on a slack line. So we've got a line that's stretched between two somethings. We don't know what they are. The person is walking on them. And we know that there's a 20-degree angle between the line and the horizontal. And then, of course, the slack line is one line, so there's going to be tension in there, and that tension is the same in both of those lines. We know the mass of this person is 65 kilograms, and the question is, what's the tension in the line? So just like we've done in previous problems, we're going to start with a free body diagram. So we'll draw a free body diagram. In this case, the object that we're looking at is the person. It has a mass of 65 kilograms. There's a tension force up and to the right at a 20-degree angle, and a tension force up and to the left at a 20-degree angle. And then there is the force of gravity straight down that's equal to the person's mass times g, which is either 10 or 9.8. And in this case, so we have some information that we can kind of read between the lines to determine that, again, this is a static equilibrium case. So it's possible that this person is accelerating upward and is about to get launched off of the slack line, or that the slack line is accelerating downward. But given all that we're told, it sure sounds like there is no motion here, and therefore there's no acceleration. And so we can assume that the sum of the forces is zero. It's equilibrium. Let's use our standard coordinate reference system, where up and to the right are our positive directions. We have two forces that we need to deal with in terms of breaking them into components, because they're not aligned with our coordinate reference system. So just like in the last problem, the y component of both of these forces is going to be equal to the overall force times the sine of the angle. And the x component is going to be equal to the overall force times the cosine of the angle. And since both of these tension forces are the same on either side of the person, they have the same equations and the same magnitude on both sides. And just like in the last problem, although we know that the sum of the forces in the x dimension is zero, if you don't have the trig skills to figure out the cosine and sine part of it, you can at least recognize that we have one tension in the positive direction and one tension in the negative direction. Sorry, component of tension in the negative direction. Those are going to sum to zero. So we know that the magnitude of those are the same, which we actually knew already. That's not super helpful. In the y dimension, the sum of the forces is still zero, but we have two positive components. We have our upward component from the left-hand side. We have our upward component from the right-hand side. And then we have the downward force of gravity. And the sum of those equals zero. And so this would allow you to find the y component of the tension, even if you didn't have super algebra skills. You'd be able to find the y component of the tension here. It's just going to be half the weight. But if what you're looking for is the overall tension in the line, if you have a little bit more trig, then you'd recognize that this is going to be t times the sine of 20 plus t times the sine of 20 minus mg. That equals zero. And at this point, we only have one unknown. We know the mass. We know g. The sine of 20 is just a number. So the only variable we have is t. So this would be solvable. And I'm not going to do the math for you, but that's something